All right, this is a video on solving systems of linear equations algebraically. We'll start with an introduction and then do a couple examples. When we're solving a system of linear equations, we're looking for the intersection point of two lines on a graph. We're looking for a point, an xy value that we could plug into both equations that results in true valid equations. And there are three different types, three different categories that we work with. And the first type is what I call just the normal situation, the most common, where there is one solution. And so that situation is where we have two intersecting lines on a graph, and they intersect in one point, and that point, the coordinates of that point, is the solution to that system of equations. Okay? The second type is what we call a consistent or dependent system of equations, where we have an overlapping line. In essence, we have two lines that have the same equation, they're the same line, and there are an infinite number of solutions. And what that's really going to look like is simply two lines on a graph that are the same line, and they overlap, and there are an infinite number of points that are common to both lines. And lastly, we have what we call an inconsistent system, is where we have parallel lines. They don't intersect, so we will have zero solutions. Okay, and that's going to look like this on a graph, where we just have parallel lines that will not intersect. All right, so let's go through some of the methods for solving these guys. The first algebraic method we're going to look at is substitution. And our goal here is to isolate for a variable and then plug what that variable is equal to in for that variable in the other equation and solve. Okay, so you have to think about which variable is going to be easiest to isolate for here. It looks like y in the first equation will be easiest. We can add y to both sides and subtract 20 from both sides, and we get 4x minus 20 is equal to y. Okay, so what we're going to do is take that 4x minus 20 and plug it in for y in the other equation. So that's going to result in this, negative 2x minus 2 times 4x minus 20 is equal to y, is equal to 10. Okay, and now what you can see is that we have one equation with one variable, so we can go ahead and solve for x and get an answer for x. Negative 2x, we're going to simplify, combine like terms. Plus 40 equals 10. We'll combine the x's on the left, subtract 40 from both sides. And then we can divide by negative 10, and we get x is equal to 1. We're not done yet, but what we do need to do is solve for y. We can plug that 1 in, x is equal to 3. I did that division wrong. Negative 30 divided by negative 10 is 3. So let's plug that 3 in for the x in my other equation. And we really can plug it into any equation anywhere that has an x and a y, but the equation that I'm circling right here is the easiest one, simply because it has y isolated for. So we have 4 times 3 minus 20 is equal to y, and it looks like y is going to equal negative 8. All right, so that would be our solution here. X is 3, y is negative 8, would be our ordered pair, our point that is valid for both equations. We can also solve these equations graphically. I'll quickly go over this, even since our focus in this video is solving algebraically. But we can just plug our equations into Desmos and find the intersection point on Desmos. So let's go ahead and do that. This is a great way of checking your work if you need to. Just type your equations into Desmos and see what you get. And so here you can see we have two lines that intersect at that ordered pair, 1.68 comma negative 1.05. And that is the solution to our system of equations. Okay. Next one, we're going to work with a second method called elimination. And elimination works really well in many word problems. If you have the x and the y terms kind of lined up on top of each other, particularly if you have a situation like this where you have a 16x and a negative 16x, if you were to add these two equations together, which we'll do, those x's eliminate. So the x's eliminate when we're adding together. A negative 12y plus 7y is negative 5y, and a negative 40 plus 30 is negative 10. Divide through by negative 5, y is equal to 2. Okay, and then what we need to do, we still need to solve for x. We're going to take that 2 and plug it in for y in either of my equations. I'm going to choose the top one. So this turns into 16x minus 12 times 2 is negative 40. So 16x minus 24 is negative 40. Adding 24 to both sides, 16x equals negative 16. Dividing by 16, x is negative 1. So my coordinate, my pair of coordinates, my ordered pair for this system of equations would be negative 1, 2. And again, that's the point of intersection of those two lines. Sometimes you're faced with an elimination problem where things don't eliminate nicely right away, and you'll have to do a little bit of math to make things eliminate. Okay, so I think maybe you can see right here, if we were to simply add these two equations together, we wouldn't eliminate a variable. So what I'm going to do is multiply the top equation through by 3, and I'm going to multiply the bottom equation through by 2. And you'll see what that turns into and why I chose to do that in a second. I'm going to try to eliminate the y's ultimately. 15x minus 6y equals negative 57. And on the bottom we have 4x plus 6y equals 0. Okay, so what you can see right now, I think, is if you were to add these two equations together, the y's would eliminate, which is nice. And we get a 19x equals negative 57. So dividing both sides by 19, x is negative 3. Okay, we can take my negative 3 and we can plug it in for x in any of my 4 equations that I have right now. Okay, I think it's strategic to think about which equation we would use, but any of those yellow highlighted x's, we could plug in a negative 3. Let's use, how about just this, that's just this second equation right here. It looks like we have some simple easy numbers to work with. So be strategic there. So this is going to turn into 2 times negative 3 plus 3y equals 0. So negative 6 plus 3y equals 0. We could add 6 to both sides. 3y equals 6, and divide by 3, y equals 2. So we were able to get an ordered pair, and our final answer to this system of equations is negative 3, 2. So the point that works as a valid point for both equations. All right, again, as we alluded to up top, sometimes we have some special circumstances, so let's look at those right now. So we have 2 final examples that we'll be working with in this video. The top one that I'll start with, I can see that I have an 8/3 y, and I always like to just eliminate fractions by multiplying by the denominator. So let's go ahead and do that and see what things turn into. So that turns into 9x minus 8y equals 45. And bringing over the bottom equation, we have negative 9x plus 8y equals negative 45. Okay, I think you can probably see some similarities there. Let's try multiplying the top equation just through by a negative 1 and see what we get. So times a negative 1 on both sides. And we get a negative 9x plus 8y equals negative 45. And I hope you can see that our 2 equations are the same equation. Okay, so this is an example, as we alluded to way up top, of this consistent dependent system. Okay, consistent meaning we have a solution, but there are an infinite number of solutions. We're dealing with the same line. Okay, so the answer here would be infinite solutions. Okay. So it's a consistent dependent system, same line. Okay. Let's look at this final final problem here, and let's try to do this using substitution. We can take, since this is equal to y, we can plug it in for y in our bottom equation and see what we get. We get a 5x minus 10 is equal to 5x minus 9. Let's go ahead and subtract 5x from both sides to start solving this guy. And we get a negative 10 is equal to negative 9. I don't know about you, but negative 10 has never and will never be equal to negative 9. It's an impossibility, it's a contradiction. So this system would be called an inconsistent system, meaning it has 0 solutions. All right, we got through it. Good job. That's a good place to stop right there.